Let's think about this for a second. That movie you just watched, your favorite song, even the image you're looking at right now, what are they really made of? Well, at the most basic level, they're all the same thing. Just a massive, massive collection of two numbers, ones and zeros.
Just try to wrap your head around that. It sounds totally nuts, right? The incredible color and detail of a film, the entire emotional journey of a piece of music, all boiled down to a simple two-part choice.
So that's the big question we're going to tackle. How in the world can this incredibly basic language create the rich, vibrant digital universe that we all live in? Well, the answer is both super simple and really, really clever.
All right, first things first. We humans have 10 fingers, so we use 10 digits, 0 through 9. So why would computers, these incredibly powerful machines, settle for just 2? It seems kind of inefficient, but there's a very real, very practical reason for it.
See, it all comes down to the physical guts of a computer. Its brain is made of billions of microscopic switches called transistors. Now, each one can either have electricity flowing through it, high voltage, or not, low voltage. It's either on or it's off. And that two-state system is super reliable. Even if the power level wobbles a bit, it's easy to tell the difference between on and off. So this physical reality makes a two-symbol system, a 1 for on and a 0 for off, the absolute perfect language for a machine.
And that right there is what we call binary code. It's a system that uses just two symbols, 1 and 0, to represent literally everything. You could say it's the native language of our digital world. And it was born directly from the hardware that makes it all run. Okay, so we've got the why. But how does a long, random-looking string of ones and zeros actually mean anything? I mean, on its own, it's just noise.
Take a look at this sequence. It's 8 digits long, which is what tech folks call a byte. Right now, it's just a pattern. It has no built-in meaning at all. What information is it holding? Well, the honest-to-goodness answer is, we have no idea. Not without one absolutely critical piece of information.
The secret sauce here is context. You see, depending on what set of rules the computer is told to use, that exact same string of ones and zeros can mean the number 84. But if the computer is using a different rulebook, say 1 for text, it can mean the letter T. It's all about the context that this software provides.
So how does 84 even become that string in the first place? Well, it's really just a different way of counting. Our system is base 10. Binary is base 2, built on powers of 2. So to represent 84, a computer just asks, what combination of powers of 2 adds up to 84? In this case, it's 164 plus 1, 16, plus 1, 4. The binary string is just the computer's way of keeping track. It puts a 1 for the numbers it used and a 0 for the ones it skipped. Simple as that.
So this is the key insight, right? By assigning numbers to things like letters, we can represent them in binary. But this idea scales up, way up. So how do we get from a single letter T to a high-definition video? An image is basically just a giant grid of tiny dots called pixels, and the color of every single one of those dots is determined by 3 binary numbers. Each number tells the screen exactly how much red, green, and blue to mix together. We're talking millions of these calculations happening almost instantly to create the image you're looking at right now. Sound is a bit trickier. A real sound wave is smooth and continuous, so you can't record it directly in binary. Instead, we use a technique called pulse code modulation. It basically takes thousands of tiny snapshots of the sound wave's height every single second and then records the value of each snapshot as a number. And when I say thousands, I mean it. For just 1 second of high-quality audio, you need to take about 44,000 of these snapshots. Your phone or computer then reads these thousands of numbers back in order, telling your headphones exactly how to vibrate to perfectly recreate that original sound. So, when you start combining the data for every pixel in every frame of a video, along with those 44,000 audio snapshots per second, you end up with an absolutely astronomical amount of data, billions and billions of bits. How can we possibly stream and store all of that efficiently?
This is where a little bit of magic comes in. It's called compression. Instead of wasting space by saying green pixel, green pixel, green pixel 30 times in a row, a smart algorithm can just say, give me 30 green pixels. It's a simple little shorthand, written in binary of course, that shrinks files down and makes things like streaming movies even possible.
So it's pretty obvious that binary is the foundation of, well, everything digital today. But is that the final chapter? Are we always going to be living in a world of just ones and zeros?
While researchers are definitely exploring other options. You've got things like ternary computing, which would use 3 states instead of 2. And then there's the really mind-bending stuff like quantum computing, where bits can be in multiple states at the same time. But for now, these are mostly just experiments. Nothing has been able to beat the incredible rock-solid stability of that simple physical on or off switch.
And that's really the big takeaway here. The genius of binary isn't how complex it is. It's the exact opposite. It's the most direct, stable, and reliable way we've found to represent information using the physical switches that power our world. Its simplicity is its superpower.
So the next time you watch a movie, or listen to a song, or send a text, just remember what's happening under the hood. It all boils down to a simple choice between on or off, true or false, 1 or 0, repeated at a scale and speed that's almost impossible to imagine. It really makes you wonder, doesn't it? What other hidden languages are shaping the world all around us?